In this video we are going to take a look at autoencoders. So what is an autoencoder? Well, it's basically a machine learning model, let's call it M, that takes some kind of input and it produces the same input, same value as the output. So what's the point of this? Because it seems pointless, right? So basically the idea is that it will do some kind of processing of the input, and during that processing it will for example reduce the dimensionality. That's the simple autoencoder, what it does. It will reduce the dimensionality of the data, and then because it needs to go back to having the same output as the input is, it has to then increase the dimensionality again. So if you draw it kind of like the dimensionality will go from like 10, let's say, to 3 to 2, something like that, and then back to 3, 5, and 10 again. So something like this. This is obviously just a very low dimensional example, but this is kind of like how it will work. And one thing you can do with this is you can do anomaly detection, because this model will have to learn a low dimensional representation of the data it has seen. So if you get some kind of unknown data, like unseen data, the reconstruction, like the output will no longer be equal to the input. So you can kind of use that as a way to see if there's an anomaly in your data. So I think we'll try to do that as well. So first let's try to import some stuff. So now we have Pytorch. So let's get the data set and let's import some plotting stuff and do this. Okay, so the data set we're going to be using is called mlist. So I think we have to say download true. We have to say, actually we have to say root is data. So this is the folder where we put things. And we do want the training data because that is the largest training set. We should also do this. How is it again? I think it is. We do need from here, so like this. Because then we can say that the transform. We want to do some transform of the data, and it's going to be a couple of things. So it's going to be. Let's turn it into a tensor. Let's start with that. I think that's the most basic. And I made a mistake here, so like that. Two tensors deprecated, right? So I thought there was something like this, and I think it's image to image maybe. Okay, so we can do that. And what do we get here? Get. Okay, let me look. Okay, so this is the new way to do it. And yeah, so that works. We get a bunch of stuff out here. And the first one is an image, and the next one is a label. So let's have a look at what is the label. The label here is just 5, which means this should be an image of the number 5. So we can go ahead and plot that and take a look. And of course that did not work because we need to a numpy array and then actually transpose it like that. So here we have something that looks like the number 5. We can put it into grayscale. Personally, I think it's a little bit boring. It's also this one. Oh, I think there's one called magma even. Let's go with magma. Okay, it's a bit more interesting. So Let's actually take a look at a couple of more examples just for fun. Maybe 4x4, and we'll slowly flatten this thing so it's easier to loop over. And then we'll just take 16 things from the data set and turn them into NumPy and make sure that they have the right shape. And then we're going to say x is I. Let's show that image here, and then we should also do x is I, and now it's called set x is off because it's so nice. Okay, so here we go. Here we have a couple of examples. You can see it's handwritten digits. So what we actually should do to see this thing where you can use it for anomaly detection, let's filter out some things. So let's make a filtered data set, which is let's say image and label for image and label and data set. If label is not equal to 4, why not? So I think we can do this, and that takes some time apparently because the data set is probably quite large. Yeah, it's 60,000, and the filtered data set only has 54,000. Well, only 54,000. So let's make that into a proper data set. So gotta import some stuff here. Data set class and data loader. We'll probably need that later. And you know what? We can also get the random split. Just for fun. So let's actually make this into a proper thing. We have to inherit from the dataset class, and we have to make an init function, and we can make it a parameter which label is to be removed. So the filtered dataset is going to be image label for image label in the full dataset if label is not equal to the removed label. Okay, and we can make this a parameter on this thing. Then we always have to define the length, and that's pretty easy. It's just the length of this list that we just constructed. Then we have to be able to get something, get an item from here, and that's also pretty easy because we just return whatever is in there. So now I should be able to say filtered dataset is the filtered, that was some autocomplete mistake. Okay, VS Code just crashed so hard I had to restart my computer, so I kind of lost my place, but now we're back. So we made this dataset class that's filtered, and what we can try just for fun is to plot a few examples from this one as well. And notably now there's no force because we removed them. So now let's try to actually implement an autoencoder. So we have to get the NN module, and we can also import that one. Oops, like this. Okay, so that's there. Now let's define an autoencoder. So it's going to be a module, and let's make a little bit of space so it's a little bit more centered. So as I said, the only restriction on this is that the output has the same dimension as the input. So let's use this module sequential. Let's easily write a couple of things. And just before we go on, let's have a look at the dataset, and we'll see like how big, how large are these, what is the shape of these input sensors. So they are images, but one way we can deal with that is we can flatten them. So let's just make something very simple that just works on vectors. Like we don't try to use convolutional nets or anything like that right now. So let's flatten it. Let's use a linear layer, so it should have 28 by 28 inputs, which I believe is around 700, something like that. It is 784. So maybe a good number here would be a little bit more than that. Then let's use tangent hyperbolic activation functions, and then maybe for fun, let's just have one layer. Let's just have this layer, and the output now should be sigmoid, because we have decided that the data has values between 0 and 1, right? We can kind of see that here where we print an example. 0, so everything is between 0 and 1. All right, so then to run this neural network, we simply pass it through this network. So here we go. And let's define a training function. So it should take a model, it should take a data set, and a number of epochs. And I think that's probably okay. So let's move the model to CUDA. Let's put it in training mode. Let us make an optimizer. Working on those parameters, and a starting learning rate. Let's just do this. It's pretty common. And then let's loop for this many epochs. And then we're gonna say for image batch and then label batch in the data loader. Actually, I would rather want a data loader than a data set. We're gonna say the output batch is running just the image batch through the model, and then the loss is some kind of loss function. So what should the loss function be? Well, since so you can make the argument for a couple of different things, but let's use binary cross entropy, because that kind of works when the values are between 0 and 1. So the target is the image batch, and the actual output is the output batch. So this is where we are saying that the output should be the same as the input, right? So let's zero the gradient. Let's run the loss backward, and let's do a step. So we can also keep track of the loss, and simply here say, give me the loss as a number. That's why we say .item, and then here we'll print like epoch plus 1. The loss is equal to epoch loss to maybe 8 decimals. And I don't know how, but somehow I guess I pressed U. Do this. And that's it. So let's make a data loader. That should be over the filtered data set. The batch size can be like, I don't know, 64. And we do want to shuffle it, that's quite normal. And let's then train. Well, we should also make a model. So I usually like to do that here. We'll make a model. Train the model for like 10 epochs. Let's try that. And that failed because the model is on the GPU, but the image batch is not. So another point is that this label batch we are not using for anything, so let's explicitly ignore it. And because the autoencoder doesn't know anything about that, it's just trying to find a representation for the data. And right, so I forgot one thing. In the end, we should make it into an image again. So maybe it's just this, and the shape should be this shape that we have up here, 128, 28. And let's see if that works. Did not work. Right, so unflattened size. So I guess we have to say 28 times 28, and then now it worked. Still there's something not working. So what happens if we just run an image through this? So does that even work? It doesn't even work. So unflattened dimension sizes, that seems correct. Maybe we need to turn this into like a kind of a batch thing. Still didn't work. Dimension out of range. Okay, let's try without this for a second. And then we'll make a test model here, and we will say test model on the data set. Just like give me the shape of that. So that works. Maybe here it's -1. Yeah, okay. So you have to do that, and this should work now, and it does work. And now we can try to train it, and it failed, which is interesting. And it fails with this error. So actually what we should do, it's probably in the dataset itself there's something wrong. And I wonder if we have like something that where we can like clip it. And it does not clamp, maybe. Clamp bounding box is not really what I want. There's no limit. Okay, so what we're gonna do is we are going to just call clamp on this, so clamp it to be between 0 and 1. And still something is happening here. And the clamp thing didn't work. Maybe this. Okay, so it's a bit annoying, but these have to be tensors, so let's turn them into tensors. And it's also annoying it takes several seconds to construct the dataset, but it is what it is. And still this one didn't work. Because I am silly. So this should definitely work, and then we say image is this, and then we return the image and the label. That worked, so let us go ahead and try to run it now. Now there's another problem. Now the model cannot be put on. CUDA for some reason. So let's try to restart the kernel and run all the cells. Okay, so after some debugging, I found out what the problem was. And essentially some of the outputs were NaN. The reason for that was that I had switched the orders of the inputs to binary cross entropy. So apparently it matters a lot that you have them in the right order. Now they are in the right order, and let's actually, so we can view the progress. Let's do something like this. And let's try not to misspell it. All right, so let's try to run it. And I made an oopsie doopsie. Because what I wanted to do here is print later batch this. Okay, now the batches are running, and actually even more, it would be nice to have like how many batches are there. So we'll do this, and here we go. All right, we gotta run that for 10 epochs. So there we are. Let's now try to see what the model has learned. So let's get 10 samples, and so we want a test image. I think we can, let's import random, and let's say random images. They are from the filtered dataset, and then we want some random choices from that, and we'll say 10 of those. Then let's actually take the image. So this dataset also has the label, so we gotta just remove the label. To make it even more explicit, we can go ahead and say there's a label here that we don't want. And then let's go ahead and plot that here. And we'll also say remove the axis because that's not very nice. And then just let's plot that. Let's see that that works. And it doesn't work because I again forgot that you have to say give me numpy and turn it into this kind of thing. Okay. So now we have a bunch of input examples here. And actually let's go ahead and say if it's the 0th, well, maybe that's a bit silly. Let's say 0, 0. The title is going to be input image. And on the other column, we're going to say it's the output image. So what's the output? Well, it's the model run on the image, and then I think we have to detach it from the computation graph, then turn it into NumPy and transpose it. And let's go ahead and see that. So output, and we can delete that. And of course that it never works the first time, because the model is on the GPU. So let's just bring it back to the CPU for this part. And that still didn't work. Probably because we have to say this has to be a view. Also didn't work. So let's go ahead and just do some debug printing. That looks correct. What if we don't have the view here? It's actually the same, which is a bit weird, but okay. So then remove the batch dimension and get rid of those. And here we go. It looks a bit weird. Maybe we can tell it to not be weird. Not really. Sometimes it helps if you say, actually give me like this. Didn't really help. Didn't really help. What if we make it smaller? Oh wait, that is the height, so that one has to be 20 and this one can be 5 maybe. That looks better. So you can see it's actually quite good already, and that's because we made a mistake. I made a mistake. So remember when I said that it should actually reduce the dimensionality? I just completely forgot about that part. So what we're going to do is we're going to say, actually, so this one was 700 something, so let's say that here we reduce it to 100, 100, and maybe even 64. So 64, 128, 128 to that. So now we need to run the training again. It's going to take a while. So once that is run, now we can see, and it should look quite a bit worse, but it doesn't look that bad. So it's reducing the images from 784 pixels to just 64, and it's actually doing all right. But you can see it makes some mistakes, but overall it's quite good. So with that in mind, let's try to actually make it really hard for it to do it. Let's say it's 16 dimensional. Then we gotta retrain, and then we can do some more plots. So now you can see, like, it clearly doesn't look exactly the same. Here it actually patched the hole. It's good at once, which makes sense. They're very simple. It's also kind of like stitching the hole, filling the hole. Okay, but remember that this model is trained on only false. A dataset where there's no false. So let's get only the false. So we'll go ahead and say image for image label in dataset if label equals 4. And then we can just, let me just copy paste this code. So we'll get some random choices from only false, and then we'll try to run that. Okay, so I made a mistake. So this is quite interesting. You can see it's a 4, but it has turned it into something that looks a little bit more like a 9, if you ask me. Because of course it hasn't seen a 4. Here, this is very clearly it's turned the 4 into a 9. And here's turned the 4 into a 9, and so on. So In hindsight, maybe it makes sense. The closest thing to 4 is a 9. But you can see it has this effect of really changing the input. In some cases, like in this one, is okay randomly, but in most cases it has changed the input a lot. So you can actually detect that, and we can go ahead and say give me 3 columns, and maybe in the third column show me the input minus the output. Then we can set the title for that to be input minus output. Somehow it failed because it's not called input, it's called image. I am silly. That also did not work because this is not a numpy array, but now it is. Okay. So it's actually a bit hard to understand that. Maybe we use the default one, which I think is what it is. And how about we just get the absolute value, because we don't really care if it's the pixel value is higher or lower. We haven't imported numpy, that's crazy to me. Alright, so now you can see it makes a bunch of mistakes here. Actually, let's go ahead and plot that here as well. So the absolute value of input minus output, and we'll go ahead and say this one because it's a bit easier to read, maybe, I don't know. And then we'll say input minus output. So these are the values that it should be good at. I call it input again, but it's image. So actually, to make it even more clear, let's say that the minimum is 0. Is that correct? Yeah, that thing's correct. And this one, the maximum is 1. So yeah, I mean, still it's not perfect, right? We can clearly see that. But if we go ahead and do the same scale here, you can see it's brighter, which is because it doesn't know really. It's not so good at reconstructing these. You can try to run the same with maybe 8. 8 is quite different from all the, well, the closest one is 3, but maybe if we remove both 4 and 9, we'd see something even more interesting. Let me actually try to run that. So let's say this is now a list, and here we are going to say if label is not, well, we don't have is, not in with labels, then we keep it. And here we'll say, actually we want to remove 4 and 9. And then I'm just gonna restart and run everything, and we'll take a look at the results when it's done. Alright, so now we have a look at this dataset that has neither 4s or 9s. So here are some examples from the dataset, and it's kind of the same story as before. It's kind of doing okay. For some reason it's kind of lowering the pixel intensity a little bit, but here's what it is. And now we can look at what happens when it tries to reconstruct a 4. This time it hasn't seen a 9, so it should be worse at it. So like this one is very bad. Some of these actually start to look like 9s for some reason. This one is becoming more of an 8. And yeah, you can play around with this a lot. So maybe the last thing I want to do is denoising autoencoders. So we saw how we could build these autoencoders to kind of be able to detect anomalies, because you can see that's something that hasn't learned to reconstruct. But you can also build autoencoders to remove noise, and that also allows you to have a higher dimensional representation there in the middle. If you remember this thing that we go 10, 5, 3, 2, 3, 5, 2, or in our example we went 700, 128, 16, 16, 128, 128, 700. If you increase this too much, it starts to just not really do anything and basically remember all the images. It does like a non-trivial thing, trivial thing. We want to do a non-trivial thing. And if you add noise to the input images and require it to remove that noise, it has to learn more like large-scale features. So let's try to make a denoising autoencoder. And actually, maybe to really emphasize that it's just a difference in training, let's take this code and say train denoising, because we don't actually need a different architecture, we just train it a different way. Right, so let's make some noise, and we can do random. I think we can do this. Let's actually have a look that this function exists, and I didn't make it up. So let's take a tensor and see if that works. So it does output something, and we can turn it into a NumPy array and transpose it like that, and we can show it. So you can see here it's just random noise, which is exactly what we want. So let's get some random noise like the image batch and device. Let's set the device, and then we're going to say image batch. We add the noise. Actually, we shouldn't do it here. We should, let's say noise the batch. This image batch clone, and then the noise batch, we add the noise, and the input here is the noise batch with noise. It produces an output, and here when we calculate the loss, the target is the one without the noise. That's the key point. So let's make a denoiser, and we just use the autoencoder same model. But now we train it with the denoising function. So the denoiser, and we need the data loader, and let's train it for 10 epochs again. So it's trained. I think the loss is a bit higher than it was before. But we can take a look at what happens when we run the denoiser here. And we should also do this. We could make this into a function, but whatever. I think it's probably a little bit worse, but I guess that's to be expected. So we can also, maybe we can try to add some noise to this. I think Is it like that? I forgot how to use. How about we just do this? Rand like image, and that. There we go. So this is not what I had hoped for. Maybe we're adding too much noise actually. Now that I do this plot, I don't understand how it even kind of worked. Let's try a little bit less. Looks better, but actually it's kind of like super easy to see the number. That's not so good. So let's define a smarter way to add noise. So maybe like we remove a little bit of the image. Right, so let's get a random spot. Well, how do we do that? Because it's like a batch. Let's do the following. So get some noise, random like image, and the device probably we need to take that as an input just. But for now it can be the CPU. And then we're going to say, actually this is, if it's higher than this, then we set it to 1, otherwise we set it to 0. And then we're going to say image is this thing times the noise. And we return the image back. So now in here we can say, just call it remove patch. Probably that's not entirely the right thing to call it, but let's call it remove pixels. Let's call it remove pixels on the image. Okay, that looks better. So you can see it's randomly removing some pixels. Quite a lot actually. But perhaps you can see it can actually kind of, it's kind of pretty good already. So let's do noised image, and here we'll take a clone, and here we will print the noised image, and then it should be a little bit more correct. It's not, because we never said image equals sorry, image.numpy.transpose. Alright, so that's pretty good. Let's take this function now. Can I do this? Probably not. Okay, so I need to somehow go back to before. Okay, so here it is. I want to put it here because we're going to use it down here. We don't need that, so we add this clone, and actually we're going to say remove pixels from that. Let's try to train it, and that didn't work because we have to say device is coder. So with that trained, we can see how well it works, and you can see it's quite, actually this one is even quite hard to see, right? But it figures it out. So you can actually teach it to reconstruct from just this input. As a human, you can kind of see it and guess it, right? But it's kind of interesting. You can teach the model to do it as well. So for the last thing, let's try to run the same model on images it hasn't seen. Like this. And And here, also over here, it's quite easy to see it doesn't have any clue how to reconstruct this, which makes a lot of sense. So even this denoising thing is even better for anomaly detection, which is kind of ironic. Like, it's worse at doing these reconstructions, but that makes it better for anomaly detection. Yeah, but I think that's it for this video, and I will see you in the next one. Bye bye.